Okay, when the object is moving into a circle or part of the circle, we say that the object is moving in that is known as the uniform circular motion on UCM. So now, this is a very unique type of motion. It is unique because when the object is moving into a circle, like you see it here, and the assumption that we are having here is that the object is moving counterclockwise. You see the velocity, so if this is the circle itself is the displacement of the object, the velocity being the slope or the first derivative of the displacement is tangent to the displacement, the velocity will be something like this. So the velocity vector is tangent to the displacement. Then what is unique on this type of motion is that the magnitude of the velocity is not changing. So what we are saying here is that the magnitude of the velocity, let's say at point A, is equal to the magnitude of the velocity at point C equal the magnitude of the velocity at point D. So the magnitude of the velocity at point A is the same as the magnitude of the velocity at point B, is the same as the magnitude of the velocity at point C, and the same as the magnitude of the velocity at point D. This, just from this fact, from this observation, the word uniform is coming from. But now I want you to think and tell me through the chat if there is a change on the velocity as the object is moving into a circle. There is a change or not? Tell me on the chat. So the change of the velocity will happen even though that the change of the magnitude of that vector doesn't change. The change of the velocity will occur because the direction of the velocity is changing constantly. So the magnitude, which very often we call it speed, the magnitude of the velocity is not changing, but since the direction is changing continuously as the object is moving into the circle, the change of the velocity will appear. And just to prove what I said, let's suppose that so the object starts at point A, and let's say that just for simplicity and to make up our point to C so that you can see that the change of the velocity is happening, and the final is at point B. So now what we are looking for is the change of velocity as the object is moving from A to B. The change, this delta, like any change, is final minus initial. So it's final minus initial. And our final is B, so will be the velocity at point B minus the velocity at point A. Are we okay up to? So now graphically what we will have is the velocity of B is this one here, velocity of B, and velocity of A is is going up, okay? Here we have it. But the negative velocity of A will be something opposite, which gives us the change of the velocity being a vector, okay? Make sense? Now, since we have the change of velocity at any moment, so we took those two moments to make it visible, but every single moment that the object is moving into a circle, the change between 2 points into the circle will appear. The change of velocity between the 2 points into the circle will appear. So now, do you think that we will have an acceleration since we have the change of velocity? So now, since we have a change of the velocity, we proved that we have a change of velocity. Therefore, we will have an acceleration. Even if you think of the formula that acceleration is change of velocity over the time that this change is happening. This change of velocity can be as a result of the change of the magnitude only, the change of direction only, and the change of magnitude and direction. The case that we are discussing is that the change of the velocity, pay attention, velocity is a vector. The case that we are discussing is as a result of the change of the direction. Is this clear, everyone? So now we say that we are dealing with a uniform circular motion, but actually the change of velocity is happening. And now let's see what is happening with the acceleration. So let's suppose that we have this as a circle, and then we have now the object is moving clockwise. So it starts at point A, and then it moves to point B, followed by point C, and then point D. So now we said that the velocity being a slope of the displacement is something like this. So this is the velocity at A, this is the velocity at B, this is the velocity at C, and here is the velocity at D. So this is the velocity vectors. We established that the velocity changes not because of the magnitude change, but because of the direction. So now the magnitude of those vectors is the same. Now, since the change of the velocity is happening, will be an acceleration that the object is experiencing. And the acceleration being the slope of the velocity time graph is a vector that goes like this toward the center of the circle that the object is moving to. So this is acceleration, 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 and acceleration. I don't want to write that yet. Okay, acceleration. So now a question for you, is the acceleration changing as the object is moving from A to B to C and D? We say that we are dealing with a uniform circular motion, but actually we are dealing with a motion that velocity changes and acceleration changes direction continuously. Okay, so it is a motion that it's kind of harder than what we have seen before, but what is not changing on the whole motion is the magnitude of the velocity, is the magnitude of the acceleration. And this is why it takes the name, because the magnitude of the acceleration and the magnitude of the velocity as the object is moving into a circle do not changes. So the word uniform comes from this. The circle comes from uniform circular motion. It's because it's going into a circle. And now, since this acceleration is a very unique, we call this a centripetal acceleration. And now I want you to tell me, what do you think that direction of force net will be on this situation? Based on the second law of Newton, what do we have is force net is equal to mass times acceleration. Since we are dealing with an object that is moving, this force net will have the same direction as the acceleration, which we called it centripetal acceleration. So force net will have the same direction as the acceleration of the object that is moving into the circle. Okay, so force net will be toward the center of the circle. Okay, force net will be toward the center of the circle. But since we are dealing with such a unique motion, again, the uniqueness of this motion stands at the fact that velocity changes direction continuously. Acceleration changes direction continuously, but the magnitude of the velocity and the acceleration stays constant as the object is moving into the circle. We call this force net as a centripetal force. Centripetal force. Centripetal force. Is this clear? Now let's talk a bit about the centripetal force. Centripetal force. Okay, let's talk a bit about the centripetal force. Even though that we say that is a centripetal force actually is not a force on its own. What centripetal force is when the object is moving into a circle, then it takes the identity, steals the identity of the force net. And this force net can be a tension of the string, can be force of gravity, or can be a universal force of gravity, or can be a force of friction. We will talk about the sources of centripetal force. But now let's clear the misconception that is in regards to centripetal force. So centripetal force is actually not a force on its own, but it is stealing the identity of force net when the object is moving into a circle or into a uniform circular motion. So what is happening is something like this, that as soon as the object is moving into a circle, then it goes into this configuration. Okay, it goes into this configuration that the magnitude of the velocity doesn't change, the magnitude of acceleration doesn't change, but the direction changes continuously. And what is happening, centripetal force goes, and I will use quotes here, goes to force net, whatever is making this motion happening, and says, move over. Now you will be called centripetal force because the object is moving into this circle and is pursuing, let's say, the uniform circular motion. Okay, so some sources of the centripetal force that you will take into the consideration of on the physics 20 are force of tension. So when you have a string that is at the end of the string you have an object that is tied with, and then you just obtain a uniform circular motion with the object, then force of tension that is on the string will be centripetal force. That may be part of it may be centripetal force, and part of it may be force of gravity. Another source of the force is when we have a friction force. So when the object is moving into a circle, a car, let's suppose, is moving into a circle, then force of friction between the tires and the road is producing or is being the centripetal force. And another one is force of gravity, which is even when we are like here, the force of gravity is mass times acceleration due to gravity, or the motion of planets. Now, since we are dealing, again, we are dealing with a very unique uniform circular motion or uniform motion, the magnitude of the velocity will be the change of distance over the time that this change is happening. Since the object is moving into a circle, what is the distance that the object is obtaining as it is completing a full circle will be circumference of the circle over time. And now we know that circumference of the circle is 2 pi r, and the time that the object obtains one full circle is known as the period. So now we have the magnitude of the velocity as the object is moving into a uniform circular motion, which you can simply say v is equal to 2 pi r over t, where r is the radius of the circle and t is known as the period or the time that the object completes a full circle. So this formula is in your formula sheet, and if you open your formula sheet now, you will see this as part of your formulas. Can you? Centripetal acceleration, on the other hand, the magnitude of the centripetal acceleration, which we can just say AC, is v squared over r. How did you do this? Is simply finding the first derivative of the velocity, which is outside the scope of this course, but take it as a word from me that the centripetal acceleration is equal to velocity squared over r. And now, substituting what we found for the velocities, that is 2 pi r over t, the whole thing squared, over r, we will have the power of 2 is affecting each term on the brackets, inside the brackets. So you will have 4 pi squared r squared over t squared, the whole thing divided by r. And now what do you have here is two fractions that are divided between each other. And when we divide two fractions, we save the first fraction, convert dividing into multiplying, and we flip the other fraction. So now we can simplify r and r here. And the centripetal acceleration, magnitude of it, is 4 pi squared r over t squared. This formula, along with v squared over r, is in your formula sheet as well. Please identify that formula in your formula. So let's work on this example. Calculate the centripetal force acting on a 2.5, mass is 2.5 kilogram object that is moving into a circle at a speed of 3.5 meters per second at a horizontal radius of 0.80 meters. So, and what we are looking for is centripetal force. Keep in mind, in order for an object to obtain a uniform circular motion, the condition is force net has to be perpendicular to the velocity. And what is happening on this case is centripetal force is stealing the identity of the force net. And centripetal force now is perpendicular to the velocity, but it is always calculated as mass times centripetal acceleration. From the formulas that we generated above, we can say that centripetal force is mass times v magnitude of the velocity or speed squared over r, or mass times 4 pi squared r over t squared. Those are the formulas, and this is how you have to think when you're dealing with the uniform circular motion. Again, the condition for an object to obtain, to pursue, to have a uniform circular motion is force net is perpendicular to the velocity. As soon as this is happening, centripetal force steals the identity of force net. And then this force net becomes, based on the second law of Newton, mass times centripetal acceleration. And then based on the formulas that we generated above, we can say that centripetal force is mass velocity squared over r, or mass 4 pi squared r over t squared. And now on this question, we will deal, or on the uniform circular motion questions, we will deal with what they are giving us in the same way as we dealt in kinematics equations. So what are they giving us, and which equation are we using? Are we using equation 1? Are we using equation 2? Or are we using equation 3? We're using equation 2 because in our situation, what do we know is mass, velocity, and the radius. So centripetal force will be mass velocity squared over radius, or 2.5 times 3.5 squared over 0.8. And now in your calculator, tell me what it's 38.28 newtons. And if we keep into the consideration significant digits, we have to write it into 2 sig digs. We can say 38 newtons, or we can say 3.8 times 10 to the power of 1 newtons. Clear? Okay. So let's take a look at this example here. A car is traveling at 20 meters per second, goes around of an unbanked curve in the road, which has a radius of 122. What is the acceleration that the car is experiencing? What provided the acceleration, centripetal acceleration? Okay, so the velocity or the magnitude of the velocity is 20 meters per second, and we have a radius of 122 meters, and we are looking for centripetal acceleration. If we go to those formulas that we just mentioned before, then we can say, based on the given information, what is the acceleration formula that we will use? Number 2 or number 3? And then we say that it's number 2. So centripetal acceleration is a v squared over r, or 20 squared over 122. And I'm avoiding the units here just because we know that what we are doing is giving us meters per second squared, or newtons on the case of the force. Okay, so I have 3.28, and if we are taking into the consideration significant digits, then we can say that centripetal acceleration is 3.3 meters per second squared. And what is providing the existence of centripetal acceleration is the fact that force net, that is, in this case, is the force of friction between the tires of the car and the street, the road, is perpendicular to the velocity that the object is obtaining. So then on this case, since force net, that is actually a force of friction between the tires and the road, is perpendicular to the velocity, then this satisfies the condition to have a uniform circular motion, and the centripetal acceleration in a uniform circular motion can be calculated with v squared over r, or 4 pi squared r over t squared. Is this clear? Okay, so here there are 2 concepts that we have to kind of elaborate into the uniform circular motion, and actually on any motion that is repeating. It's the period and the frequency. So period is known with the capital letter T, and it's the time that the object completes one full circle, one full revolution is known, in the other words. And the units for periods are, for period is seconds, because it's time. And frequency, on the other hand, is how many circles or part of the circle you complete in one revolution. Okay, so what is the number of circles or part of the circle that you complete in one revolution? So pretty much is how often do you see the object, you focus in one point and then you say, how often do you see the object moving through that point in 1 second. So the frequency is with a lowercase f, and since it is circle per seconds per time, so the units are 1 over s, or now they are well known as the hertz. So 1 hertz is 1 over s. The relationship that is happening between the frequency and the period is they are inverse of each other. So frequency is 1 over t, or t is 1 over frequency. You have those formulas in your formula sheet. Can you please go to your formula sheet and identify those formulas for me? Now we'll deal with this example. If the frequency of the rotation for an object is 4.0 hertz, what is the period of rotation? So they are giving you the frequency as 4.0 hertz, and they are asking for the period. Now, period is 1 over f, so will be 1 over 4 hertz. And the units here will be 1 over seconds, or 1 times seconds over 1. And now when we are multiplying, will be seconds. And this is, again, showing what it is. And this will be 0.25 seconds. What those numbers are telling us is that you see the object passing through a fixed point in the circle 4 times in 1 second. And what this number is telling us, 0.25, is telling us that the object completes 1 circle in 0.25 seconds. Does this make sense? Okay, so we have the velocity, the magnitude of the velocity of the object that is moving into a circle is, we said, 2 pi r over t. But now since 1 over t is the frequency, this will be 2 pi r f. So those are the two formulas that we use for the velocity. On the other hand, what we said about the centripetal acceleration is v squared over r, or going through calculations, we said that is 4 pi squared r over t squared, or 4 pi squared r f squared. I do not think that those two last options that you see here are in your formula sheet. Now we have a question here. If an object is traveling in a circle, as soon as it is traveling in a circle, means that the object is moving into uniform circular motion, which in your mind should be like the condition to have a uniform circular motion, that is force net perpendicular to the velocity, is satisfied. Now, traveling in a circle with a radius 5.0 meters has a frequency of 6.0 hertz. What is the speed of the object? So again, now we can either find the period and then use this formula here, or knowing that the period is 1 over f, we can say that the speed will be 2 pi r times f, or 2 pi times 5.0 times 6.0. And then the unit works perfect, and we can see what is, using the calculator, what is the volume. Meters per seconds. So the velocity will be 188 meters per second, or you can say 1.9 times 10 to the power of 2 meters per second. Is it clear? Okay, so now we have another example, is centripetal acceleration of a stone being whirled into a circle at the end of 1.75 meter string at 350 meters per second square. What is the frequency of the rotation? So what is given here is that the radius of the circle is 1.75 meters, and the accelerations, which is a centripetal acceleration, is 350 meters per second squared. And what they are asking for is the frequency. So find out which formula are we using, and then let me know on the chat. Because this is the formula that we will use, because this is the formula that connects what is given with what we are looking for. So in this case, the centripetal acceleration is 350. 4 and pi squared are constants, and the radius is 1.75 times f squared, which gives us f as the square root of 350 over 4 pi squared times 1.75. Using your calculator, tell me what is the value of the frequency. Now let's move to the other example. So who is the same example? So now what we will see is we will see a situation of the vertical uniform circular motion. So when you have an object that is moving into a circle that is perpendicular to the ground, what do you see as the front view is something like this. The object is going from point A to point B and so on, okay, moving into the circle. In the vertical uniform circular motion, what do we study? Is we see what is happening with the object at the top and at the bottom. So the situation that we will discuss is you have a string that at the end of the string of one of the strings is the object with a certain mass is tied on, and what you are doing is you are rotating and making a uniform circular motion with velocity, magnitude of the velocity v, constant, as we said before. Okay, is the situation clear? Like in everything that we do when we are discussing the forces, what do? Is we draw the free body diagram at the point that we are discussing it. Let's see what is happening at the top first. Okay, so at the top, the object is moving into a circle in a uniform circular motion. But the object, which is the object of our interest, is the object moving into the circle, is represented by a dot. And then we have force of gravity that is always going down to the center of the Earth. Now, when we are at the top, the string goes like this. Okay? Therefore, the tension, following the rule that we have said about tension from the object along the string, will be as well something that is going down. Now, since, and this is everyone, please, attention, since everything is happening toward the center of the circle, when we are drawing the free body diagram and talking about the uniform circular motion, going toward the circle, toward the center, sorry, toward the center is considered to be positive. Everything that is outside the circle is considered to be negative, and everything that is toward the center is considered to be positive. When we are at the top, at point A, the center is somewhere in here. So on this case, both force of gravity and tension will be positive. Now, force net, as in every case that we have said, is the vectorial sum of all the forces that the object is experiencing. And on this case, we have only those two forces, force of gravity and tension. Okay? Since those two forces are both going toward the center, force net or force of gravity will be positive and tension will be positive as well. But force net, since it is moving into the circle, the identity of it will be stolen by centripetal force, because we said that centripetal force is not a force on its own, but it steals the identity of force net when force net is perpendicular to the velocity or the object is moving into a uniform circular motion. Okay, from here, we can solve for tension as being centripetal force minus force of gravity. Okay, and now we know that centripetal force is mass velocity squared over r, and force of gravity is mass times acceleration due to gravity. So this is the relationship of the tension at the top. Clear? Now let's see what is happening when the object is at the bottom of the circle. At the bottom of the circle. We are on this situation when the object is at the bottom. So now the string is from the object to the center. This is the string. Now let's draw the free body diagram at the bottom of the circle. So we'll start with the object of our interest represented by a dot, and then we'll draw the force of gravity, which is always going down, because it is always like this. Force of gravity starts from the object and going down to the center of the Earth. On the other hand, what we have here is the tension. But notice what I'm saying, that the tension is always starting from the object going along the string, and along the string is going up. So this will be the tension. Okay, and keep in mind that when you are standing here, the center of the circle is somewhere up here. So now we said that going toward the center is always positive because everything is happening toward the center. The centripetal force is toward the center, force net toward the center, acceleration toward the center. So therefore, toward the center is important, and we call it as a positive. Now, force net is always the vectorial sum of all the forces that the object is experiencing. And in this case, we have only those two forces, force of gravity and tension. Now, force of gravity going away from the center, is it positive or is it negative? So now force of gravity going away from the center is negative, and tension going toward the center is positive. Oops, is positive. What about force net, which is the centripetal force? Is it positive or is it negative? Is positive. And since the object is moving into a circle, then we know that it's positive, force net is positive because it is moving in a circle. Therefore, the condition to have a uniform circular motion is satisfied, meaning that you have a positive force, centripetal force toward the center. So now from here, let's find tension as centripetal force plus force of gravity. Or if we substitute the centripetal force as mass velocity squared over r and force of gravity as mass times acceleration due to gravity, you will have a different formula when the object is at the bottom of the circle. And you probably have experienced this, and if you haven't paid attention, I would please you to grab something, grab a string, tie an object at the end, one of the ends of the string, and rotate it, and then you will see as the object is going up, you feel the tension in your hand is less and less until it reaches the top, and when the object is down, when it's moving down to the circle, you will feel the tension as increasing and being the highest at the bottom. Does this make sense? We have here an object is swung from the end of a 0.5 meter string into a vertical circle. If the time of revolution, meaning the period, is 1.2 seconds, what is the tension in the string at the top of the circle and at the bottom of the circle? Okay, so as I said, you can take those two formulas at the top, or you can, tension is equal mv squared over r minus mg, and substitute what is given. Mass is 1.8, and now this is the acceleration. Okay, you can use the other formula, so m 4 pi squared r over t squared. So this will be times 4 pi squared times r, 0.5 over 1.2 squared minus 1.8 times 9.81. You can do this, or you can go through all the steps that we went to figure out what is the tension at the top and what is the tension at the bottom. And initially, I think that will be a good idea to do that, but then after that, you probably will be okay to not. Okay, so applying the formulas, you will have tension at the top, tension at the bottom as 7.0 and 42.3 newtons. Even from the calculations, you can see that the tension at the top is smaller than the tension at the bottom.